Take a seat and get something nice to drink. I want to start with the Fibonacci sequence. As you may or may not know, the Fibonacci sequence is the sequence of numbers 0, 1, 1, 2, 3, 5, 8, etc. And the rule that it follows is that each term is the sum of the previous two terms, and we begin with initial conditions 0 and 1. So I'm going to write that as the nth term is going to be the n minus 1th term plus the n minus 2nd term. And the first and the 0th term is 1, and the 0th term is 0, and the first term is 1. So given these two rules, our initial condition and our transition rule, we could figure out any Fibonacci number that we want. And this is a version of what's called a difference equation, because this transition rule expresses the relationship between the terms at different points of the sequence. And there are some really neat applications of this difference equation idea. So an example is a population hierarchy. Let's say we had 3 kinds of population in our population. We have the children, the adults, or the economically active, and the elderly, who I'll call seniors. And SN, EN, and CN are going to describe how many of each kind of person do we have at the nth generation. So we're going to have a unit of time of generations. And so we're going to need a transition rule for how these age brackets in the current generation relates to the previous generations. And we're going to need an initial condition for the initial state of our population. So the initial state, initial conditions, I'm going to say it's going to be sum S naught, E naught, C naught. And they're going to be greater or equal to 0. And then the transition rule, let's have something like seniors nth generation is going to be some proportion of the adults of the previous generation who survived. And adults nth generation is going to be some proportion of the children of the previous generation who survived. And CN children is going to be some proportion of the adults of the previous generation who gave birth. So these alpha, beta, and gamma, they're parameters. They're kind of knobs we could tweak in our model depending on the characteristics of our population. So this alpha, beta, and gamma, they're proportions. So I'm going to put them between 0 and 1. So this transition rule is going to tell us the terms SN, EN, CN in the future if we start at the initial conditions and just keep going through. And this is a system of difference equations, but I'll call it difference equations just the same. And the question I'm interested in, I think it's quite natural to think why, is what is the nth term? What is the state of our population on the nth generation? So n could be like 1, 10, or 100 or something. And we might want to know this because maybe we're a demographer and we want to predict how our population is going to go. We want to see if it's going to become an aging population, if our population's going to die out. Maybe childcare costs are going to increase, or maybe we're going to have a labor shortage because there's too much there's too many dependents, too many seniors and children. All kinds of things we could think about. And that's going to rest on being able to calculate this rule quickly. Just by using the transition rule directly, it's going to take us about n calculations, or time proportional to n calculations, to figure out the population on the nth generation. But we could do better. And to do better, we're going to go back to something that's simpler and may only seem kind of related right now. So I want to talk about exponentiation. So I'm going to take two positive numbers, a and n, two positive integers, two positive whole numbers, a and n. And I want to find what a to the n is. And a to the n is, by definition, a times a times a times a times a, n times in total. And the straightforward algorithm for doing this is just, well, multiply a by itself n times. So a to the n, I'm going to say, is equal to a times a to the n minus 1. And a to the 1 is going to be equal to a. Okay, nice. So when our algorithm sees a to the 4, it's going to say, okay, well, the exponent is not 1, so I'm going to go to the first case and say, this is going to be a times a to the 3. And since the exponent's not 1 again, I'm going to do this case again until I get to the exponent is 1. So I have a times a times a times a. Nice, and it looks kind of like a line, a tree shaped. Okay, and this is going to take time proportional to about n steps, because we have n multiplication symbols in here. We're going to make this recursive call n times. And in some sense, this is going to be our transition rule. This a to the n equals a times a to the n minus 1 is our transition rule from moving from a to the n minus 1 to a to the n. So instead of Fibonacci, where it's like fancy, we have to add the previous two terms. To get to the next term of our powers of a's, we just multiply by a. It's also a transition rule. And there's a fast algorithm for doing this. I'm going to call it fast exponentiation, fast exp. And its insight is that we could save work by splitting our power, our n, into roughly two different blobs, and have those blobs be pretty much the same thing. So once we know one of the blobs, we just need to multiply that blob by itself, and we don't have to compute the other blob. What I mean is, if we had some a to the power of 2k, so where k is a whole number, so 2k is going to be an even number, that's going to be a to the k times itself. So to figure out what a to the 2k is, we just need to know what a to the k is. Then we just take the result and multiply it by a to the k again. And so if you imagine doing a to the 8, it's going to want to figure out a to the 4, it's going to want to figure out a to the 2, it's going to want to figure out a to the 1. And once it knows those, it just multiplies them appropriately, and we get the answer with much fewer multiplications. To make this a complete algorithm, I'm going to cover the odd case as well, since this is only the even case. The odd case, we're going to say, okay, we can't split exactly in half, so we could take something off and then split it in half. A to the 2k plus 1 is going to be a times a to the k times a to the k. So this is going to be doing essentially splitting it in half, except once we split in half and did our trick of only figuring out one of the blobs, we tack on another a. And of course, we need our base case that a to the 1 is equal to a. So let's try this on a to the 4 again. It's going to look at 4 and say, oh, 4 is even. So it's going to go to this case and say, well, this is going to be a squared times a squared. And we're only going to look at the a squared on the right, because once we know it, we just need to use the same value for the a squared on the left. So it's going to look at the a squared on the right and say, okay, well, we're going to split it again, since it's even, like so. And we're done. So it's going to get a, multiply it by itself to get a squared. And then we already have this a squared, this blob of work we'd already done. So we just recombine, and we're done. And this only took 2 multiplications instead of 3. And in general, this is going to do much better for bigger numbers. Let's do an example. And before we do that, let's check out the shape of this tree. I'm going to expand that a squared. I'm going to say, okay, well, that a squared is going to be a times a. Isn't this nice? So this fastexp algorithm, instead of having a tree that's shaped like a line, it has a balanced binary tree. That's the visualization of this, I think. Maybe it's no surprise that the more symmetrical expression for the same calculation is going to get us the faster algorithm. Well, maybe it is a surprise. It's nice. It's the big number, so 21. A to the 21, that's going to be, okay, it's odd, so we're going to do a times a to the 10 times a to the 10. It's going to look at the a to the 10 and say, okay, well, the a to the 10 is going to be a to the 5 times a to the 5. And a to the 5 is going to be a times a to the 2 times a to the 2. And a to the 2 is just going to be a times a. So you can see this big tree. And once we've expanded it, it's going to look quite balanced. This a to the 10 is going to fill itself up. This a to the 5 is going to fill itself up, and so on. And this is only going to take us 1, 2, 3, 4, 5, 6 multiplications instead of 20 multiplications. That's a good job. To do a slightly more formal running time analysis, our kind of by definition original exponentiation took us about n steps to do a to the n, whereas our fastexp, it's roughly having the power by 2 for every multiplication. And it keeps having the power by 2 until we get to 1. So the amount of steps is roughly how many times could we have n by 2 until we get to 1. Well, this is going to be about a function called log base 2 of n, which is the answer of 2 to the power of what is equal to n. And this is really good, because when we double the input, the output's only going to increase by 1. If you double the input, we only need to have it one more time. So have it one more time to get to 1. Whereas for a linear function like n, like our first algorithm, when we double the input, the output, the running time is roughly going to double. So for big numbers, this is going to make a huge difference. And for how huge? For n equals 4, n is about 2 times log n. For n equals 65,000, n is about 4,000 times log n. And for n about 4 billion, n is going to be about 100 million times log n. So even if you had a computer that's 100 million times faster for each multiplication, once we get to a big enough n, the log n is going to wipe the floor. The n is not going to stand a chance. It's going to it's not a matter of hardware. This is why algorithms are good. So let's take a break, have a drink, and think about what could this possibly have to do with difference equations. And also as fastexp, why didn't we split the power into 3 roughly equal blobs, or 4 roughly equal blobs, or some bigger number of roughly equal blobs? Could that have made a faster algorithm? A challenge to you is to show that actually any kind of splitting into roughly equally sized blobs strategy is going to be at most as good as splitting into 2 blobs. All right. So now we're going to generalize. And we're going to generalize fastexp so that we could work with cooler things. By cooler, I mean more things, and also cooler. So I'm going to talk about functions or functions have the same meaning as transition rule. And functions, I could compose them, which means I could do them one after another. So I'm going to have a function t, u, and v. And t composed, I forgot to mention one thing. So earlier, the reason that we could reshuffle our kind of line-looking tree and make a balanced tree is because of a key property of multiplication. It's called associativity. What associativity says is that a times a in brackets is equal to a times a times a. And this looks like what is this? This is obviously true, but it's not true for everything. And it has a nice graphical representation. The left-hand side looks like a tree that leans to the right, and the right-hand side looks like a tree that leans to the left. So what this associativity law is telling us that we could reshuffle the tree however we like, which is why we could reshuffle our line-looking tree and make it into a balanced tree, and that's just beautiful. And so we want to look for other things that have this associativity property. And that brings us to function composition. So the definition of composition is u composed t is just doing u after doing t. And function composition is associative as well. So v composed u composed t is equal to v composed u composed t. An analogy, I like this one, is making instant noodles. So t is going to be putting in the noodles in the bowl. U is going to be spice packets. V is going to be pouring in the hot water. So the left-hand side says, okay, we're going to put in the noodles, put in the spices, then put in the hot water. Right-hand side says, we're going to put in the noodles, then we're going to put in the spices and pour in the hot water. And this associativity is saying that those two orders are the same, which makes sense because we are doing the same thing. So that's neat. And so if we had a transition rule t, a function t, and we wanted to find where we end up after we do the function over and over again, maybe n times, that's a kind of exponentiation. We have this associative operator, this composition, and we're applying, and we're kind of putting n t's together using it. And I'm going to write that as t to the n. And so the exact same fastexp algorithm applies. Instead of peeling the onion one layer by another layer, we could break it up into two roughly equal blobs and then recombine them and only do pretty much half the work every step. So how would we write that in general? We would say that t to the 2k is going to be t to the k composed t to the k. T to the 2k plus 1 is going to be t composed t to the k composed t to the k. And t to the 1 is going to be t. Well, same algorithm as before. And it still works because we could still reshuffle the tree around since composition is associative. And here we bring back our initial conditions, maybe x naught. So this could be whatever. It could be our initial state of our population. For the case of a to the power of n for like multiplication, our initial condition is going to be a to the power of 0 is 1. So actually a to the n is equal to kind of t to the n and then applied to 1. Where in this case, tx is going to be a times x. So So actually, our earlier exp is a special case of this function version, where our transition rule is just we multiply by a, and our initial condition is we start with 1. And this is good news, because with this kind of function formulation, we could talk about Fibonacci, we could talk about the population pyramid. Since with those things, it makes sense to talk about a t that's just a bit more complicated. And a kind of subtle note I haven't really ironed out myself is we want it so that when we compose two functions, that the composition, the cost of applying that composed function is going to be the same or roughly the same as applying each of the individual parts of the composition. So we don't want t to the k composed t to the k to be twice as expensive as applying t to the k. We want it so that when we compose, we don't make the function any more complicated. And for the case of exponentiation, that's true, but that's not true in general. And you could ask in the comments if you want to know an example. So we have Fibonacci. And with Fibonacci, the transition rule is transition is gonna take kind of our state, our pairs of numbers, our adjacent Fibonacci terms, and bring them to the next Fibonacci terms. I'll take fn minus 1, go to fn plus 1, fn. And the thing about t is that it's linear. Linear means basically it's nice. You could check out 3 Blue 1 Brown's linear algebra series to learn more. And what I want to highlight here about linear functions is that, or linear transition rules, is that you could write them out as a matrix. You know everything you need to know about the transition rule by just tracking a grid of numbers. In this case, the transition rule is that t of fn and fn minus 1 is going to be equal to the matrix 1, 1, 1, 0 multiplied by fn minus 1. So this t, its entire information is captured in this matrix. And the second piece of good news is to compose linear functions, we do something called matrix multiplication, which takes some time, but it's only a constant amount of time. It doesn't depend on how big we're raising t to the power of or something like that. It just takes time proportional to the cube of the dimension of the matrix, which the dimension is like how many rows it has. And so to figure out the nth Fibonacci number, we just need to figure out what t to the n is, which is the same as figuring out what 1110 to the n is. And here we use fast exp. And I'm going to do 1110 to the power of 21, figure out the 21st Fibonacci number. And what it's going to do is it's going to compose t with t to the 10. So this is the odd case, so we tack something extra on. And then it looks at the remaining 10 and says, okay, that's t to the 5. And t to the 5, it goes to odd case again. Then we go to t squared, compose t, blah, blah, blah. Okay, so this is the same tree as earlier. And it's going to give us a bunch of big numbers. And the point is that this raised to the 21 gives us 17711 10946 10946 6765. Numbers aren't really important, even though I said that's what's important. Well, I mean, whatever. So then this t to the n, we just need to apply it to our initial conditions, 1, 0. And with a bit of matrix operations, we know that that's going to give us a t to the 21 applied to this. It's going to be the first column of the matrix, 17711 10946. And since t to the n applied to f1, f0 is going to give us fn plus 1, fn. f21 is the bottom entry here. And we've done that quickly. We could do we could find the nth Fibonacci number kind of in log n time. So I want to do more examples, but this is really going over time. And some thoughts to have before you go. Have a go at applying this technique to the motivating problem of our population pyramid. How do we write out the matrix of our population, and can we do some cool stuff, like figure out the 1,000th generation of something? And if you'd seen my video on folds, think about how this relates to folds on natural numbers. So fast exp, I think you could write it as an equation, kind of a theorem involving fold on natural numbers for associative replacements of the successor. It's kind of like associativity lets us reshuffle the tree. And as a challenge, multiplication is a kind of exponentiation, because it's the same as applying the transition rule of plus something every over and over again. Like a times b is applying the transition rule. Plus b, a times. And all that applied to 0. So does this let us implement a fast multiplication algorithm on natural numbers? Don't know, but have some tea and see you next time.